Hey, Young's double slit experiment was really just the first example of interference that we've looked at. Historically, it's the first one that was ever figured out, and it's still the one that is the simplest to describe and the most readily apparent, with that nice spectrum of dark and bright fringes from two slits. But interference shows up all over the place in the world. Interference of waves shows up all over the place, and not just out of the lake or out of the ocean, and not just in a refrigerator box carried around the park one day, like you saw in the video from Veritasium. It also shows up in your childhood. You get soap bubbles, and if we were still meeting in person, we would actually go out to the quad on a sunny day and play with soap bubbles. And we would look at all the lovely colors that show up in soap bubbles. Those swirly greens and blues and yellows and pinks that you see, that is interference. That is known as thin film interference, because those soap bubbles are made of what we call a thin film of soap. We'll get to that. That second example of interference. The first one was Young's double slit, and now we're looking at another case of interference. A lot of the same language is going to come up, path length difference, that kind of thing is going to come up, okay? But before we get there, we have to talk about this little topic that's buried down there in section 24.3, phase shift due to reflection. And the connection between this and soap bubbles and interference is not obvious right now. But it's a topic we have to at least address quickly before we get on to the second case of interference, thin films. All right? So let's talk about this, what this means. Phase shift due to reflection. All right. Let me give you an example here. Suppose we have a rod, like say a vertical pole, okay? And we tie a rope to it. But actually, we don't really tie a rope to it. Where's my pink? We don't really tie a rope to it. First, what we do is we put a ring around the pole and tie the string to it. Woo, that sound in the studio, man. Woo, kind of hurts. All right, so what we have is a rope tied to that ring, which is free to slide up and down the pole. Okay. And what we're going to do is we're going to take that string and we're going to kick it. We're going to put a wave and send the wave down it. This is kind of like the situation that happened when we took a slinky out into the hall earlier in the semester. We're talking about waves, transverse waves and longitudinal waves. And I sent a wave down the slinky and it went down to the other end, whoever was holding it, whatever fine volunteer that was holding it, and it bounced back. The wave returned, it reflected and came back towards me. Okay, this is kind of like that. But this time the end is loose, okay? And we're going to send a wave down this rope. It's not a slinky in this case, it's a rope. So we're going to send a wave down it. You can do this. You can go out with, go out into my front yard with a garden hose. Take the garden hose and pull it up and pull it down, and this wave will travel right down the garden hose. It's a lot of fun, and you should do it. You can do it without getting close to anybody. I encourage you to do it. Okay? Now, if the end of the string, the rope here is loose, now you can't do this demonstration you can't do this because the end of your hose, but I wanted you to go out and do the hose thing just so you could see the wave traveling down it. So the wave is traveling down it. If the end of the rope is tied to a ring that is free to move, when that wave bounces back, it will reflect Okay, it will reflect, it will come back. Here's the ring. It will not be upside down. It will be right side up. And I meant to draw it about the same size. There's really no change in shape or size here. Ideally, it would be the same size and everything. Okay? It's going to reflect. Okay? Now, in this case, now suppose we do something a little different. Suppose we have the same rope, the same post. Wow, those sounds, man alive! And we're going to tie it. This time, we're going to tie it directly to the post and fix it there. So this end will not be free to move up and down as this one is. This is free. And it will move up and down as the wave gets to the end before it reflects. It will slide up and down a little bit. But in this case, it's fixed. Okay, good. Fixed. Now if we send the wave down it, like that, when it reflects and comes back, it's going to be upside down. It's going to have undergone an inversion. Okay. That one's fixed. This one is free. This is known as a phase shift. And when we first did the slinky deal in the hallway, the volunteer was holding her end of it. So when it reflected, it was fixed end, so it reflected on the opposite side. And if we were together, we would go out in the hall and do this with a slinky. So you'd see this. This is the case of the slinky on the floor. There's a phase shift. It gets inversion. There's an inversion of the wave. It's actually known as a 180-degree phase shift. The reason we call it that is not important for us today. But sometimes you'll hear me call it that, a 180-degree phase shift, a full phase shift. It goes from upright to upside down. It goes from positive to negative, okay? All right, so what? What does this have to do with soap bubbles or anything with light? All right, what does it have to do with anything? Next lecture, I'll make it short and I'll tell you then. Bye.